Hi guys. As I promised, I'm going to do a quick review of Chapter 5. Just as a word of caution here, I'm going to fly through quality assurance and then slow down just a little bit in calibration methods, but we're going to quickly go through all of this. So why is quality assurance so important? Well, you've probably seen, most recently in probably the last 10 to 15 years about all the potential for re-examining forensic cases, drug cases, DNA cases, things like that. And so if you can go back and you can talk about your quality assurance, you can stop those kinds of things from happening. So here are the basics. Quality assurance is what you do to get the right answer every time, right? Or to at least have a very good way in which you can determine how accurate or precise the answer is. So you come up with a process, right? You have these use objectives, you write those out, you have specifications from either your from the court, from your customer, from a source, right? And then you do an assessment and whether or not the specifications were achieved. So the goal, right, is to make sure that your results meet the needs of whoever that customer might be. So you have to think about your raw data, you have to think about any kind of treated data, and then you have to think about results. In other words, your interpretation of the data. So how good are the numbers, and what are you going to do to make sure that the analytical procedure is appropriate? You've got to determine the number of samples, how many should you have, degradation, what are the costs, the restraints, and then, what accuracy, what level of accuracy do you have to have, and what rate of false negatives or positives might be acceptable. So medical implications are obviously the highest, right? So a false positive result when, let's say you are being tested for cancer and you falsely identified that you have cancer, what can happen there? And so it's a matter of what the allowable level is, right? So again, you have to choose the method according to what you're looking for, right? If you're looking for cancer, you might choose a much different method than if you were looking for levels of something in pet food, right? So you have to you have to make sure that you're considering the sensitivity of the method, and then blanks, right? So blanks are important to all of us. There's something that you identify as a method blank, a reagent blank, and a field blank. So those are different sources of what that matrix is, right? Method blank, everything except analyte. Reagent blank, very similar to the method blank, but it might not have all the preparation done to it. And then a field blank, again, where you take a sample from the field that you know doesn't contain any of your analyte. So one of the things that you're going to need to remember, especially throughout the real-world project, is that the matrix is everything in the sample other than the analyte, right? You're going to need to show whether or not you can recover. So even if you don't think there's any of the analyte in your sample, can you put some in there and recover it and say, I recovered 99% of that? So that's a spike. So I've mentioned a spike several times before. You're going to need to do that in your real-world project. We're going to skip this one and skip that as well. So large numbers, right? If you're dealing with large numbers of samples, you have to consider all of these different things. Method drift, what happens over the course of time to your method. Calibration check, you can't use a calibration curve from 8 o'clock in the morning, at 10 o'clock at night necessarily. SOPs have to take all this into consideration. So the assessment, right, was part of this, and get the data, verify the results, and then document everything that was done, and then use those use objectives that were created, and make sure the method is fit for the purpose, right? There need to be control charts in laboratories. In other words, what's going on with your system over the course of time. And so you would set, let's say, your mean plus or minus 2 standard deviations. If it goes beyond that, then you would stop. You would stop using the method, try to figure out what was going on, and try to fit that. Standards are really important, right? You guys are using standards in your real-world projects. These are some of the institutions that generate or certify standards. Here's a few more, right? And then there's method validation. We did a little bit of, we talked a little bit about these kinds of things in the statistics chapter, but you're going to have to make sure that the method is acceptable for what you're doing, right? And all of these things, selectivity, linearity, accuracy, precision, range, limit of detection, limit of quantitation, and robustness have to be taken into account. So selectivity, right, is it specific enough for the analyte that you're looking for, or are there going to be interferences? Linearity, how good is that calibration curve? Does it fit to a least squares? Your R-squared value tells you the fit, and anything that has 2 nines or more is probably going to be acceptable. Residual plots, the difference between calibration data and the least squares line. So, what's lying outside of the line, and why, and what are you going to do about it? So, quinine on the left, quinine on the right, quite different. So linearity, right? So linearity, this was the quinine from the left, a very linear response in this case. However, in this case, a non-linear response, and so you have to consider what's going on here. The consideration might be to fit this data to something other than a line. So if you consider fitting it to a quadratic, you get this quadratic expression out. And then the R-squared is great. But is that really a reasonable thing to do? Well, you look back at your procedure. If the fluorescence is zeroed using distilled water instead of the sulfuric acid, maybe it is, right? So you have to fit your procedure to what you're going to use as your way of interpreting. Nearness to the truth, if you've got some certified reference material, that's always the best. 2 or more different methods, comparison is important. And then a spike, right? A spike can do wonders. Standard additions we'll talk about in a little. So, how accurate is the test? Well, this is, something that you would talk about your recovery of a spike and say, okay, I can do this. I can recover this percentage consistently, and it's 99% or 100%. This is showing this percent recovery. You probably can't read this very well, but what this is saying is that you would measure. So first of all, you would take a sample and you would spike it with a known quantity of analyte. Okay. Now that sample has been run prior to the spiking, so you know what you identified in that sample. Let's say it's magnesium. You got 10 parts per million in there. you spike it with 10 parts per million. Now you come back and you find out what your reading is. Your reading is, let's say, 19.99 parts per million. You take out the 10 parts per million that you originally identified as being in that sample, and now you've got 9.99 parts per million that you recovered, right? So you put the 9.99 over the 10, right? And then times 100, and you're going to get the percent recovery, right? All right. So again, that's something you want to make sure that you're doing in real. So different kinds of precision, your instrument, precision of the instrument is always important. Assay precision, in other words, if the same person repeats it several times with the same equipment, how precise is it? If you have different people in the lab doing this, and then if you do comparisons of inter-laboratories. So all of those are ways in which you can describe precision. Range is important because you're going to get samples in that are either smaller concentration or higher concentration, and this idea of linear range is what allows you to look at a large range of concentrations. Dynamic range is where there is a response, right? So where there's a measurable response, but this linear range is where you would be willing to work. And robustness is, is the method affected by changes in small changes in parameters like temperature and things like that. Again, back to the linear, right? You want to create the calibration curve, right? Y equals mx plus b, and that's given right up here, right? There's the y equals mx plus b, and then you also want to generate an r squared that says that the closer to 1 this is, the better. If you hit 1, that means you have round-off error or it's made-up data, because the goodness of fit will go to 29s if you do that. If you do that in your spreadsheet. The r squared, again, this is how we determine how good that line is, that fit. All right, so let's talk a little bit about detection limit and quantitation limit. So detection limit is LOD, or limit of detection, right? Limit of quantitation is the quantitation limit. So what are we going to use for these? Well, the detection limit is given right here, and that is, the limit is the y that you can get out, that is the average of the blank plus 3 standard deviations of the blank. Okay? So the minimum detectable concentration down here, right? And this is essentially saying the same thing, 3 times the standard deviation over the blank, okay? And so 3 times, it's also oftentimes written this way, and this is more instrumental, 3 times what we call signal to noise ratio. Okay, that's supposed to be a times there. So 3 times the signal to noise ratio is our blank, or I'm sorry, our limit of detection. And then we go on to, sorry, I gotta get this out of here. Let's go into the quantitation. This is what we would call, or we're getting closer here, right? So if you are going to report something, right, it has to have a limit, right? I mean, you're not going to report 0. You're never going to do that. You're going to say, well, it was below my ability to detect. That's a reporting, right? But even then, what we would say is that it is below the limit of quantitation, which is what we would say is our reporting limit. So again, back to this idea of LOQ now, and LOQ is now a little bit higher. It is now 10 times the signal to noise ratio. Okay, that 10 times then is well above the limit of detection. You wouldn't want to work at your absolute bare bones limit of detection. All right, so let's quickly look at standard addition. Why would you do this? Well, in standard addition, oftentimes you have what's called a messy matrix, right? And so what you're going to do is you're going to take, instead of building a calibration curve in distilled water, you're going to build a calibration curve in the sample. That's basically what's going to be done. It's because of the matrix, and so if you take the matrix effect out, you end up with something that is built on top of, right, any matrix effect. You have to look this up in the book, but basically standard addition takes into account what else is in there, and so what you put in there, right, the kinds of dilutions that you made as you put that in there, and then finally the standard addition, you can create that calibration curve and back calculate to find out how much of the original sample is in there. Okay. Let's just keep going later. One of the things that I do want to highlight here, though, is the idea that over here you can create this calibration curve, right? And this is the standard addition. This is the actual fit to the line. And notice that the B value, right, is not 0, right? Because there's something in there. There's sample, or I'm sorry, there's analyte in that sample. Well, we could show this mathematically, that if you go back here to the x-axis, that's actually the concentration that was originally in there. And again, we'll do that a little bit more in the so you typically would do this in a spreadsheet, right? And you'd write your equation. This is kind of the way it looks. I kind of like this picture just because of the way it says, okay, you're going to start with unknown in each flask, and so that's the unknown in each flask. You're going to add an amount of a known, right, the standard, and then everything goes to the same volume, and then you have this plot over here, again, going back to the x-axis, you get the actual value. Let's get through this and get to internal standards. Internal standards, so standard addition is one way to deal with a messy matrix. Internal standards is a little different. It's a way that you can deal with a misbehaving known, if you will, right? The known does not behave the same way all the time, in changeable concentration, in changeable conditions, anything like that. And so you might put an internal standard in that is very similar to the analyte, however, it's not the same. Your assumption then is that it will behave the same, okay? And then you create a relationship between the response of the internal standard and the response of the analyte. It's really useful when the quantity of the sample analyzed or the instrument response varies, because the internal standard to your analyte. That relationship does not change. Okay, and I think we're finished talking about. This. This is chapter 5. Hope it's helpful, and have fun.